had this at this weird age.
Okay.
Okay, yeah.
No, I haven't.
We're on?
Yep.
Okay. Hello, everyone who's in the room and outside the room. I'm very happy to introduce today's seminar speaker, Evan Meeker. Evan Meeker joined us here in fall of 2021, working in my group. He got his bachelor's in physics and astrophysics from University of Minnesota in the Twin Cities, Minnesota, where he's originally from. From there, he has had a lot of fun experiences before getting here. For example, from 2016 to 2017, he was a planetarium education assistant at the Bell Museum of Natural History. He was then a field crew member working for the Conservation Corps of Minnesota in Hanover, Minnesota, doing such things as natural environment restoration, removing invasive species. And he also worked, after that, as an environmental and GIS technician with the New Hampshire National Guard, doing more flora and fauna surveys. Then started here working in my group on a project on marine heat waves funded by the NSF. This is also a project where he's got to interact a lot with folks at the other UW, the one in Seattle, with Luann Thompson and her group, as well as with the folks at the National Center for Atmospheric Research, Emily and Beppenmeyer. And since then, he's done a lot of very cool stuff. He's been very involved in the department, so most of you are probably familiar with him and how many questions he asks during seminars. If not, here's Evan. And he has started on a fellowship from the National Defense Science and Engineering Graduate Program this fall, and he will be telling us today about his work on both the NSF project and since then on the fellowship on marine heat waves, the predictability, and their relationship to the Pacific Decadal Oscillation. So with that, take it away, Evan.
Thank you, Liz. And thanks to, again, the rest of my collaborators, Luann Thompson in Washington, Anna Deppenmeyer, and Steve Yeager at NCAR, and Dan, who is our very own here. And today I'm going to be talking about predictability in the North Pacific, looking at extreme events, climate modes, and seasonality. Oh my. And I want to start by talking a little bit about what I mean by predictability. So this department has a really long history of doing weather forecasting, and forecasting the weather has been an integral part of the field for decades. With modern weather forecasting, being able to predict out to 10 or maybe 14 days in the future before the chaotic nature of the Earth system starts to take over and you lose the ability to get good predictable skill. On the other side of things, we have these climate projections that have been trying to nail down exactly how much our climate system is going to respond to the amount of human emissions and other human-caused forcings in the system. And these are two sides, these weather forecasting and climate projections are two sides of the timescales at which you can do predictability. But they're really two ends of a whole spectrum of timescales along which you can do predictability. And on the one end, you have these weather forecasts, which you can get out to a certain point. And on the other hand, you have these long projections where the external forcing of the system is dominating the signal that you see. But in between, there's this wide range where you aren't quite far enough forward to get that external forcing, and the variability of the system is dominated by internal dynamical structures. And it's at these timescales, seasonal to interannual, or S2I timescales, that I'm interested in talking about today. So why do we want to predict the climate? And why do we want to predict the climate at S2I timescales? Well, there's been a lot of work showing that drought in the hydrological cycle has predictability at these timescales, and that has a lot of impacts on things like crop growth and food security, water availability, and dam levels are additional points. There's also been a lot of work showing that predictable changes in sea surface temperature can impact the intensity and number of tropical cyclones. And if you're a policymaker or maybe an insurance company that in the next year or so is trying to figure out how much money you expect to spend on these sorts of events, it can be extremely helpful to get even a general idea of how much of these sorts of things are going to happen. By the way, that's me. I went on disaster relief in 2018 after Hurricane Florence hit the Carolinas, and I'm taking furniture out of a house before it gets muck and gutted to get all of the wet drywall that's in the house out so that mold doesn't grow in it. And I want to emphasize again that I'm not trying to predict an individual storm or the specific day at which something's going to happen. I'm trying to predict the background state of the climate that can inform you about how likely these sorts of things can occur on a seasonal or interannual time scale. Okay, so just to explicitly state it, my goal is to assess the predictability of the North Pacific Ocean, its extremes and variability at seasonal to interannual timescales. And the way I'm going to do that is using a state-of-the-art, fully dynamical model based on the Community Earth System model, or CESM. And my talk is going to have two major parts. The first is a case study on the predictability of the 2013 to 2015 Northeast Pacific marine heat wave, and the second part will focus on the predictability of the Pacific Decadal Oscillation. First, I want to talk about how you go about predicting the climate at these timescales. So at SOI timescales, predictions are made using initialized physical climate models. So these are the same climate models that are used to make those projections, but you initialize them using the observed state and then run them forward in time. These models tend to be run monthly and predict up to 6 to 12 months out. And I've got an example of a whole list from the North American Multi-Model Ensemble of a number of physical models that have more or less these parameters. And the model that I'll be using specifically is called the Seasonal to Multi-Year Large Ensemble, or SMILE. And this is a research prediction system that was made available in the last year and a half or so that uses CESM as its core that it runs on. So if you aren't familiar with how fully coupled climate models work, this is just a simple schematic. And what you have is a bunch of individual parts of the system, such as the atmospheric model or the ocean model here. And these will run their physics internally, and then at a given time step, they send information to the coupler. And these are all of the surface conditions for each of these models. So the coupler handles telling each model what the other models do, and then they all will individually run forward and then come back. And this is if you do this right, you can get a pretty good estimate of the climate system. But the problem for prediction is that the state of this climate system is going to be random compared to our actual climate. And so to force the system to be in something that is specifically the Earth's climate, there's a number of different ways you can do it. The way that SMILE starts off is by replacing this atmospheric model with an observational forcing system, specifically a modified version of the 55-year Japanese reanalysis. And what this does is the atmosphere, these observations obviously aren't getting any information back from the model. They're just running on the actual Earth system. But they can force all of the other components. And over a long period of time, you can set up your model so that it's you can set up your simulation so that it's in the same state as the observed Earth system. And this is called, in case I mention in the future, this is called a forced ocean CA simulation, or FOSSI simulation. And SMILE initializes its predictions off of this. So now I've got this FOSSI simulation, and I want to start a prediction. The way that I do that is up to whatever the time period that I want to initialize. So let's say I want to start a forecast today. So that's time 0. And then I'm going to be working on a monthly time scale, so I'll be looking 1 month into the future, 2 months into the future, etc. So at that initialization, we have our observational forcing of the ocean and sea ice models. And then at that initialization point, I replace the observational data set with the atmospheric model. And so now from this point forward, we're able to run a fully coupled model into the future. And we'll often run multiple members of this model so that we get an ensemble of possible predictions that we can average over to improve our prediction skill. So if I did that today, I would call that a forecast. But I can also start that initialization at any point in the past. And if I started, let's say, a year ago, I would run it forward, but I would already know the right answer. And so when I run these hindcasts, the point is to try to assess the prediction skill of the system, because otherwise you would have no idea whether or not your forecast is any good. And so SMILE specifically is initialized 4 times a year in February, May, August, and November, and I'll be using these colors to refer to these initialization dates for the rest of the talk. And it's run from 1970 to 2019, so we have 50 years of information. Something that's special about this data set is that it's run out to 24 months. And like I said, a lot of these operational forecast models will only run out to 12 months. And so running out to 24 months is more computationally expensive, and saving the data takes more space. But you get to see more of the seasonal variability in how well your predictions do. Finally, each of my initializations is a 20-member ensemble where I start with round-off level errors and then let those errors propagate forward, so I get a range of predictions into the future. And then I will be showing the ensemble means in a lot of these plots where I take an average over those ensemble members to get my prediction. So with that, I'm going to move on to the first part of the talk, the predictability of this marine heat wave in the Northeast Pacific. And first I want to just briefly go over what a marine heat wave is. So basically, it's the same thing as an atmospheric heat wave. It's just a high percentile of the possible observed values of temperature. And in the oceans, these will be on the order of usually like a couple or a few degrees Celsius. So they really aren't as large in magnitude as atmospheric heat waves. But the variability of the ocean itself is much lower, so they still can have extreme impacts. And just to give some examples, the ranges of species habitats might shift depending on marine heat waves. You can get impacts on fisheries if there's die-offs due to heat. Like I said previously, warm sea surface temperatures can provide additional energy to storms. And finally, coral or kelp, things that can't move, can have massive die-offs if there's an extreme enough event. So I'm interested in a specific event, one of the largest, most intense, and longest-lasting marine heat waves that's ever been observed. And this event got so much attention that it eventually got the nickname the Blob. And the nickname stuck both in the general community and the research community, and so I'll be referring to it as the Blob. I feel like there's a lot of blobs in the climate system, but this one is the Blob, and so no one else can have it. And I'm showing on the left here a picture of sea surface temperature anomalies in January 2014. And what we see is these deep anomalies up to or above 3 degrees Celsius off the coast of the Pacific and the Gulf of Alaska, with some mild cold anomalies or climatological state along the coast here. And on the bottom left, I've got a time series, both of the observations of this event from OISFT and the FOSSI model representation of it in the dashed line here. And we see that there's this peak in 2014, and it goes forward for over 1.5 years in this region that I'm averaging over. But an important thing about this event is that it wasn't stationary. So here I've got a GIF showing the initial magnitudes of the blob anomalies. And what you see is that over the course of the year, you have this persistence off in the Central Pacific, but by the time you get to the next winter, so watch as we get to like October, November, you start to see these anomalies form more along the coast rather than off in the Pacific. And by the time you're a year out, you actually have negative anomalies out in the open Pacific and these warm anomalies along the coast. And when people talk about the blob, they're referring to this entire event that includes this dynamic evolution of where the anomalies are occurring. And you also see that at the end of this GIF, it kind of feeds into this 2015 El Nino event. What's up, John?
Evan, how deep is the anomaly?
Yeah, that's a really good question. And in this talk, I'm going to mostly be focusing on the surface, but I have looked at the depth structure of the blob, and what you see is that for most of the occurrence out in the open waters, it's an anomaly that starts at the surface and then works its way down into the depth structure. I haven't looked as much along the California coast, but my guess is that there's a larger depth structure there that you would see out in the open.
Thanks.
And just to make sure I say this out loud, SST observations are all from the OASST data set, and the anomalies are all calculated from a monthly 1981 to 2010 climatology with the seasonal cycle removed. Okay, so the first question I want to ask is just, is the blob predictable? And that's not really that specific, so let's make it more specific. I want to ask, is the magnitude of sea surface temperature anomalies associated with the blob well predicted in our SMILE prediction system? And second, is the pattern of SST anomalies associated with the blob well predicted, that evolution of where the anomalies occur? So starting with the magnitude, here I've got that same region that I'm averaging over for my time series, and the same observed and FOSSI representations of our system. And one thing I want to point out is that although the FOSSI does a good job of representing sea surface temperatures in general, there are cases where there's extreme events where it can start a little bit below the observed temperature. And this is important because the predictions are initialized off of the FOSSI model. So sometimes you're starting your prediction even below the absolute peak in the magnitude in these extreme cases. And then these colored lines that I have are, again, February, May, August, and November initializations for 2013, the year before this peak in the blob. And what we see is that even when they're initialized during these warm anomalies earlier in the year, they die back down closer to a climatological state. And these are the ensemble means of the prediction, but we can look at the ensemble spread as well. And what we see is even when we include all of the members, none of them capture the magnitude of surface anomalies at the peak of this event. And there's a multi-month miss here. And this is pretty impressive because not only does at least one member usually capture anomalies in this region, but when you back out to look at it farther, a multi-month miss like this is actually unique in this region for the entire SMILE data set. So to answer the first question, is the magnitude of the blob well predicted? No, at least not at the peak of its onset in this region. And so now I'm going to move on to the pattern. And so now we're looking at a spatial extent of the blob. And what we have on the left here is my FOSSI observations, so I'm using these as a stand-in for observations. And on the right, I have the predictions initialized in November 2013. So these, so here we have our first month of lead time, and going down the map, we're going forward in prediction space. So we initialize, actually, this is more like half a month, but I just simplified it to one. But what we see is we initialize, and close to our initialization date, we have the magnitudes pretty well represented, and we have the spatial pattern well represented. And that's good, because when you're initializing it, you want it to at least start off the same way. And as we go forward in time, we see that the magnitude in the observations completely blows out the scale that I have here. And this is the ensemble mean of the November 2013 initialization. And you don't see that large anomaly, but the pattern still matches pretty well. However, as you move forward, going from 4 to 6 months and then up to 7 to 9, what you start to see and what we saw in that GIF was that the warm anomalies start to move towards the coast, and you start to especially see these cold anomalies that occur in the Western Pacific. And by the time you get to a year out, these cold anomalies have moved from the Western Pacific into the Eastern Pacific, and the warm anomalies in the observations are totally are trapped along the western coast of North America. However, in the predictions, what we see is that there's really no evolution of the spatial signature of the blob. And we can quantify this sort of pattern that we've been talking about with something called pattern correlation. And what you see is that we start off with the patterns matching roughly well in the first few months, but there's this decrease in the pattern correlation compared to the average across all of 50 years. And by the time we get out to a year out, we're doing worse with our pattern correlation than any other year in the entire time series. So each of these gray lines is one November initialization, and at a year, the November 2013 initialization is the one that does the worst of any. So this pattern is not well represented, the evolution of the blob. from this off-coastal pattern to along the coast. And something interesting is that if you initialize just 6 months later, once you start to have these cold anomalies intrude into the Pacific, this is from May 2014, and what you see is you do a much better job. So you're going along up to a year out around average, but then in the second year, you start doing at or better than any other initialization. And so this difference between doing the worst in 50 years and then just 6 months later doing the best in 50 years tells you that there's something about this shift in the blob that is just not well predicted by the system. And so we see that the magnitude isn't well predicted, at least at this peak, and the pattern isn't well predicted, at least prior to the onset of the peak of this event. And so the next question would be, why isn't the blob well predicted? And in an alternate universe, there's an Evan that starts talking about the different physical mechanisms that lead to heat transport in the system, and we would probably do a heat budget breakdown, and I would talk about Ekman transport, and I would talk about sensible heat flux and latent heat flux, and I would talk more about the depth structure, sorry John, and it would be a very good talk, I'm sure, and I am also sure that John would ask me a question about the anomalous pressure ridge, and I wouldn't be sure how to answer it, and that would be that. However, in this universe, I looked at this pattern of anomalies here that stayed pretty much exactly the same through the whole prediction. And I thought, that kind of looks like the Pacific Decadal Oscillation. And that made me change my question here from why isn't the blob well predicted to why isn't a sign change in the PDO well predicted? And that leads me to the second part of my talk. So I should probably start by talking a little bit about what the PDO is. And it was first defined by Manto et al. In 1997 as the first EOF of monthly sea surface temperature anomalies between 20 north and 70 north. And EOF is an empirical orthogonal function, which is a statistical method that you can use to find the pattern that maximizes variability within the system. So the PDO is a pattern of maximum variability in the North Pacific on these timescales. And it has quite a long time scale. So this is just a time series of the PDO, I think from ERSST, not OASST. But what we see is that prior to the onset of this blob event, we had been in a negative PDO more or less since 2005. And in general, the decadal part of Pacific decadal oscillation refers to the fact that it has very high memory and is slow to change. And I just wanted to point out again that at our 2013 initialization, we really see this negative signature where we have positive anomalies off the coast in the Gulf of Alaska, and some negative anomalies or maybe climatological values along the coast. And this is the opposite sign of our signature of the PDO here. And so that leads to a negative value of the PDO. But a year later, we've got these cold anomalies in the Pacific, and the anomalies associated with the blob are all contained along the Pacific. And that shift is also associated with a shift in the sign of the PDO within 1 year from -1 to positive 1.3. And so that's a huge shift for these, a huge shift that then maintains that shift for quite a while as well. And this map that I'm showing here, this is a regression of sea surface temperatures and sea level pressure onto the PDO index. And there's two things I want to point out here. The first is that you see there's a clear connection to El Nino. And the second is that there's this anomalous low sea level pressure that's associated with the sign of the PDO. And past studies have shown that both of these connections are actually lead the PDO index, and that the PDO isn't truly a mode of oscillation, so it's kind of a misnomer, but rather a combination of multiple physical modes that you statistically gather together when you do this EOF analysis. And so I want to talk a little bit about each of these strong correlations that pop out when you do this regression. So I'll start with El Nino, or the El Nino Southern Oscillation, and I won't go into too much detail, but what I will say is that El Nino is the single largest source of predictability in the climate system on seasonal to interannual timescales. And you might have heard a lot about this recently because right now we're actually going into the peak of a fairly strong El Nino. So I didn't need to even go find a schematic of El Nino. I just took the sea surface temperatures from a couple days ago, and what you see is these warm anomalies in the tropical Pacific. And this has a time scale of roughly like 9 months to a year that this very predictable physical oscillation will occur over. And the other thing I want to mention about it is that there has been a large body of study on something called the spring predictability barrier. And that's basically saying that El Nino predictions that are initialized prior to around March quickly lose skill beyond boreal spring. And if you want to hear more about that, I recommend going and watching the recording of Dan's talk from a few weeks ago. But I'll leave it at that for now. Moving on to that low pressure system, I just wanted to talk a little bit about the climatology of pressure in the region. And there's a strong seasonality. So we see in the summer months, we get this subtropical high pressure system maximize. And then as we move to winter, we see that the Aleutian low really grows and has a maximum in January. And previous studies have shown that the PDO index is mostly correlated specifically to wintertime sea level pressure anomalies. And that in the summer, there's not really a connection between anomalies in this region and what the surface temperature is doing. Okay, so moving on to PDO predictability. There have been efforts since pretty soon after it was first defined to predict the PDO using statistical models. And this is an example of from 2003 where the PDO is modeled very simply with just the memory of the initial condition of the system as well as some ENSO force variability. And I won't go into the detail, but they do a pretty good job. Even in 2003, like this representation was one of the papers that first showed how ENSO was forcing the PDO. More recently, there's been work using more complicated statistical methods such as linear inverse models. And I don't want to go into too much detail, but we can see that at leads of up to 9 months, they're still getting correlation values that are above 0.5. And I'll get more into what that means later, but just remember that we are getting, from statistical models, correlations above 0.5 at least 9 months out. On the other hand, the last paper, or the most recent paper I can find that goes into detail of PDO predictability using a dynamical system similar to the one that I'm using here was in 2012, and it was by some folks at the Climate Prediction Center. And there's some differences between what they're doing here and what I'm about to show you. The first is that they only go out to 6 months, and so they really don't get to see this interannual predictability and the differences there. And the second thing is that we have this very quick decline in skill. So in the model in 2012, we had anomalies going below 0.5 at just 6 months. So these are not doing as well as the limb models that were coming out even years beforehand. So my goals are to examine the seasonality of PDO predictability in a cutting-edge dynamic prediction system, and to use some of these simple linear models, not to predict the PDO, but to understand the sources and limitations of predictability in my complex dynamic system. And before we do that, we have to actually calculate the PDO in SMILE. And here I'm showing the first EOF of SST anomalies, calculated both in my FOSSI simulation as well as in OISST. And I'm just showing this to show that the FOSSI simulation does quite a good job at representing the PDO. And when you plot the index time series, they have a correlation of 0.95. So I'll be using the FOSSI representation of the PDO moving forward, and I just wanted to show that it does quite a good job of capturing the variability and pattern of the PDO here. Okay, so I calculated the PDO index and the PDO pattern in my FOSSI simulation. And now I want to go calculate it in my hindcasts. But I run into a problem here. The hindcasts are only 24 months long. And that's just not enough time to capture the variability of the PDO, which has this time scale that can be many years or even decades long. And so the solution is pretty simple. It's just to project the EOF that I calculated from the FOSSI onto my hindcast anomalies. And what I mean by that is just that I take the EOF or eigenvector or just the spatial pattern of anomalies here, and I project them onto my matrix that has the predictions, where M is my spatial dimension and N is my time dimension. And what I get out of this is just a prediction time series that's kind of like a principal component, if you're familiar with that, but it's only 24 months long, and that is what gives me my predictions. Yeah, John?
Evan, could you kind of cut your data set into places where you have transitions in the PDO side? And would they be less than 24 months? And could you do EOFs on that?
You could do an EOF over all of the hindcasts as well, and that is something that the 2012 paper that I showed did. And you do see that there's a decay in what the PDO pattern comes out as as you increase in lead time. I don't think they specifically looked at times where that transition is occurring, but I think that would be something interesting to look into. Okay, so when we do that, we can get our predictions of the PDO index. And here, this is a lot like the SST anomalies that I was showing, except now my black line is just the observed PDO index, and my predictions, just all in red here, is my little spaghetti plot of my predictions, 24-month long predictions of the PDO. And so now that I have these, I can ask my more specific questions. The first is how skillful are PDO predictions in SMILE? And then I want to look into the seasonality of this predictability. And finally, I want to look at how SMILE predictions compare to simpler statistical models of the PDO. So just starting with a sort of qualitative assessment, we see that there are, overall we do a pretty good job of predicting the PDO, but there are places that stick out where we see a poor prediction. And what is usually the case in these poor predictions is the PDO index has a quick shift into the opposite direction in the observations, but the predictions just keep going in the same direction that they started in. And just to zoom in on our example of that related to the blob, this is the 2013 to 2014 shift. And what we see is that the PDO index is negative or close to 0, and the predictions continue to keep that climatological state. But in reality, we see the shift up into the positive index. And even after you have that positive index, you have the anomalies for the next few initializations trying to dip back down to the climatological state before it starts to stick. Okay, so for the rest of the talk, I'm going to be using a more quantitative method of looking at the scale, and it's something called anomaly correlation coefficient. And this is just a correlation between the observed and predicted anomalies, and it's a measurement of how well my predictions co-vary with the observations at different lead times. And so just to give an example of that, I've got some predictions that I initialized in August, and so what I have here at +1 month, this is the actual observed PDO value in September for every September going forward. And then this is my prediction in that same September, 1 month forward. And we see that close to the initialization date, we have quite high correlation values. But as you go forward in time, you start to lose that correlation. And it's literally just a correlation between these two time series, between the red line and the black line here. And you can imagine that if you had an ACC of 1, you would have a perfect prediction. And if you had an ACC of 0, you would be doing no better or probably even worse than if you just picked random noise as your prediction. And so I can do this for every initialization and at every lead time. And what I get is a plot that looks like this, where on the x-axis, I'm going forward with lead months, and on the y-axis, I have my ACC values. And again, the colored lines are February, May, August, and November, and then I've just taken a mean to show generally how well the predictions are doing. And what we see is that there's a scale decrease over time, and that's expected going farther in the future. It's harder to predict these things. But what we see is that the correlation remains above 0.5 out to the first year. So in SMILE, 10 years after the last paper that looks into this sort of thing, we're doubling the amount of time that we're getting prediction skill above 0.5. And so just to reiterate, our prediction skill is high in the first year, about 0.5, and qualitatively we see that poor predictions are occurring during rapid shifts in the PDO index. So now I want to move on to the seasonality of PDO predictability. And here I've taken those same lines that I showed you before, and all I've done is I've added an offset to them so that they all line up on the same month. So February here is here still in the same place, but then the May initializations plus 3 months, plus 6 months, and plus 9 months. And I've also colored in the plot with these same colors so that you can easily tell which season we're talking about here. And the colors match with the initial months of my colored lines. And the first place I want to point out is this period of slow decline that occurs in the summer months between June and October. And what we can see is, so for example, you can initialize in May and you get an initial skill decrease in the first month or two, but then it really levels off. And when you initialize in August 3 months later, it drops down actually to the same point that the May initialization is at. And then they stay at the same, more or less the same predictive skill almost for the rest of the time series. And this is in contrast, we see these periods of rapid decline where, okay, so now May and August are basically on top of each other, and they both decline quickly from November going through to January. And the November initialization, despite being started 6 months after the May initialization, drops almost down to the same level in just the first couple of months. And my speculation here is that this rapid decline that we see during the winter months is related to increased random forcing from the atmosphere during the season. So we know that the Aleutian low is maximized during the season and that the jet stream and variability from the storms are increasing during this season. And that's my theory for why this is happening here. The second period of rapid decline occurs in March through May. And again, we see now in all of our initialization months, independent of when we start them, so February is 9 months farther along, but we see the rapid decline in each of these initialization start times during the same months. And February doesn't do quite as bad in the first couple months as November, but it is the other start time that does particularly bad in the first few months compared to the summer initialization days. And this, I believe, is related to the spring predictability barrier that I mentioned earlier with El Nino. And I'll get more into that in the next part of the talk. So, we see that there's a stable skill from June through October and rapid declines in these 2 periods, November through January and March through May. And now, I want to see how these predictions compare to simple models of the PDO. And I'm going to start with a first order autoregressive or AR1 model, and then I'll extend that AR1 model and do 2 experiments where I include forcing from El Nino. So, how do you go about modeling the PDO as an AR1 process? So this is a pretty simple one-dimensional prediction, and it goes back as far as Hasselman and talking about stochastic models. And there's a couple things I want to point out here. So we're trying to predict the PDO at the next time step. And the only information that we're going to include is the PDO at the previous time step plus some random forcing. And this value here, this phi value, is a regression parameter that's a measurement of how much information is retained between your previous time step and your current time step. In my case, I'll be using a monthly time step. And the noise forcing here is assumed to be normal in nature. And when I do a prediction, you can imagine that one way to do a prediction is to do 1,000 or 10,000 ensemble members and then average over them, and that gives you a better prediction. And if the shape of this noise forcing is normal, then that should average out to 0. And so my best prediction is actually just setting this to 0 and just using the memory from the initial condition, which turns this into a sort of exponential decay towards the climatological mean state that takes longer or less time depending on how much memory the initial condition or the system contains. And so when I go through observations and calculate this parameter, I get a value of 0.91. And this is equivalent to the lag1 autocorrelation of the PDO. And so that maximizes out at 1. And this is quite a lot of memory being maintained between time steps in my simulation. So what does it look like when I go and run this model? So now I've got, again, these are the dynamic predictions, and I've just split them up into 4 boxes: February, May, August, and November. And when I include my AR1 predictions, what we see is just the first thing that you notice is that the predictions do almost as well as my dynamic predictions. And this is kind of amazing because the only thing I've done is include the PDO at the initial condition and then run it forward. And so this is telling us that most of the prediction skill that we see in our full dynamic system is just a prediction of persistence. And there are some areas where you do a little bit worse. So for example, right here, it dips below, or in the second year of the August initialization. But likewise, there's a couple places, and they usually are occurring in the winter to spring transition, where my AR1 process is actually outperforming my full dynamic system. And I can run a significance test on these statistical predictions just by running a Monte Carlo simulation. And what we see is because the deterministic prediction without noise forcing tends to be a good prediction, our deterministic prediction lies along the top of that significance scale. Okay, so we see with our simple AR1 model that persistence is explaining most of the prediction skill in the system. But now I want to move on to extending it using values from El Nino. And I'm going to run 2 experiments. The first, I will use values of El Nino that are predicted using my full system, and then, or using SMILE, and then put those into the statistical model. And in the second experiment, I will use the observed, that's the wrong word, I will use the observed El Nino for the prediction all the way forward. So if everyone can get out their Wilkes textbooks and open up to page 233, we can go over multiple linear regression. And really this isn't that much more complicated than the AR1 model that I'm using before. Now all I've included one extra one-dimensional parameter, and this is using the Nino 3.4 index. And now I just have 2 regression coefficients that together tell me how much information I should have in my next time step of the PDO. And these are a little bit less straightforward to interpret than just the autocorrelation when I only had the PDO. But what we see is that our phi1 is still quite high, 0.89. And so most of our prediction is still coming from persistence, but it's modulated by the strength of the Nino 3.4 index. And so first, I want to do this model where I use the initial condition of the PDO and just run that forward. And then at each time step, I use the ENSO value predicted by SMILE to try to predict the next time step of the PDO. And what that's sort of doing is saying, we're trying to find how much of the predictability of the PDO that we see in SMILE is caused just from how well SMILE can predict El Nino plus the initial condition of the system. And so when I run that model, what we see is now we match the predictability in the first year of the system almost perfectly. And it does the best in February, but it's still doing quite well for all the initializations. And we match the seasonality that we see in these anomaly correlations for the whole time series. And if you remember before, we saw that the AR1 model was going above the prediction here. And now when I include El Nino, not only is it matching this rapid drop, but it does start to diverge away at this time period from my full prediction. And so what we're seeing here is that a difficulty in predicting El Nino is associated with this rapid skill decline during these months. And you can see that this divergence occurs during the spring times in all of the predictability. So we're doing almost as well here until we hit May, and then it starts to diverge. Same thing here. Okay, so now instead of using the NINO 3.4 index predicted by SMILE, I'm going to cheat a little bit and use the observed NINO 3.4 index. So this is like, what if I could perfectly predict El Nino going out to 24 months? So it's cheating, and so I'm going to call this the perfect ENSO model. But it's telling us kind of an upper bound on what we think we could predict the PDO as if we were able to perfectly predict El Nino values. And when I do that, what I see is that there's almost no change in the first year. And it's not until the second year, again, it tends to be in spring of the second year, that you start to see this divergence where there's an increase in my predicted model versus the PDO. And so I kind of see this as an upper bound, a theoretical upper bound on how well you could predict the PDO if you could perfectly predict El Nino, which is a more deterministic mode of oscillation. Whether or not that's actually possible is a completely different question, but this is like a theoretical upper bound. And so again, just to go through all of this, we see that most of the skill in the SMILE system is just explained by persistence of the initial conditions. Once you include the predicted El Nino, we also capture the seasonality of that predictability. And if we use the observed El Nino, we only improve our predictions compared to the dynamic system in the second year. And so bringing this back to looking at the blob, now with all this information we have about trying to predict the PDO, we can look and say, okay, so we started our predictions and we had this sign for the PDO index, and in reality we were at the opposite sign a year later. But our prediction just predicted persistence. And usually that's a good prediction. And so we are predicting the PDO well, except in cases like this, where there's a fast shift. And so that's telling us that there's some sort of external forcing that is not predictable, likely due to atmospheric processes, that was very important for the evolution of this spatial pattern. And with that, just to go over all of my conclusions again, we see that the magnitude and pattern of the blob are not well predicted, at least prior to the start of the 2013 Pacific Marine heat wave. For the PDO, we see that there's high skill and predictability in the first year. There's these rapid skill drops in the winter time, which I believe are associated with the atmosphere, and in the spring, which I believe are associated with the spring predictability barrier of El Nino. And when I compare it to simple models, we see that persistence explains most of the prediction skill that we see. When we include ENSO, we can capture that seasonality. And finally, using the perfect ENSO model, we only improve our prediction in the second year. So thank you, and with that, I'll take any questions.
Okay, Hamish.
Nice talk, that's really cool. You convinced us that the blob looked a lot like a negative PDO. Does that happen every negative PDO? Do we get like a blob-like structure?
So that's a good question, and it's a very difficult one to answer, because again, because of the time scale at which this index evolves, there's only a few examples in the observations where this sort of thing even occurs. So I'm sure there are studies of how the PDO is modeled for thousands of years in models, but our models, we can only verify them using reality to the extent that we have those observations available. So this is certainly something that there are analogs to farther in the past, but there was nothing to this extent prior to 2014. Now there actually have been recently large persistent marine heat waves in the same region since then. And so that's a question of whether or not these sorts of things will become more common in the future. That's another avenue you could go down.
In the back. Yeah, right.
So, I have a question. I don't know much about, forecasting the blob or anything like that, but if you were to look at other climate models that also have a coupled system, do the ones that resolve ENSO better do better
I have not done an intermodal comparison for that, and I don't know if anyone has, but I think that is a really good question. And I do know that the representation of El Nino does change quite a bit between the models. And there are arguments that spring predictability barrier. There are arguments that it's just intrinsic to the system itself, and there are also arguments that it has to do with misrepresentations of the extent or timing of El Nino events. So that's certainly something that would be interesting to look into.
I'll just quickly add, SMILE system is on par with the NMME and the operational systems in terms of the global patterns and El Nino. Rudra, next.
Yeah, Evan, great talk. I had a question when you showed on your slide 49 or 50 that the sharp change in PDO are usually not well predicted.
Mm-hmm.
I see that there are other incidents where it undergoes kind of a sharp change from negative to positive. Can SMILE is it able to predict that? And do you think that shifts are always associated with sharp shifts in ENSO as well? That's why you're missing the prediction.
So something that I think is interesting about this specific time period is you see this shift that then continues on for at least a couple of years. A lot of this noise, again, that's probably due to like short time scale noise forcing on the system. And if you my guess would be that you don't predict this because that is very very short time scale, and it goes back to the climatological state. So the prediction would probably do well in predicting that, oh, it's going to quickly return back to something closer to zero. So this sustained increase here is one of the most interesting pieces of this.
Let's see, Larissa, I think I saw you last time.
Yeah, so nice talk. The implication is if we wanted to predict the blob better, we should focus on improving our ENSO predictions. Am I understanding that correctly?
Yeah, I think that's part of it. And there's also
Or
part
it
of
might
it,
not be predictable.
yeah, part of it is an understanding that, especially for such an extreme event like this, it might just not be predictable. And there is literature looking, so part of the reason I wanted to look at the PDO was because it is a much better studied phenomenon than the marine heat waves, which that definition only came around within the last few years. And there are studies that show that shifts in the sign of the PDO tend to be unpredictable, while the duration of PDO in one sign or the other is more predictable. And so again, that has to do with if there is a shift, it can be caused by random forcing or unpredictable forcing, but that the ocean tends to want to stay in the same state that it starts in. And so it's only with these random events that you can shift from one regime to the other.
So is that a yes or a no?
I think the answer is that the blob is not predictable because it was forced by atmospheric noise. And that saying that the PDO shift is not predictable because it was forced by atmospheric noise is a very similar statement. Maybe not exactly the same.
Okay, so you're not arguing we need to predict ENSO better to predict blobs. You're arguing that the blob is intrinsically unpredictable.
Yeah.
Okay.
And that's impressive because it sticks around for a long time, but the onset is quite quick compared to the persistence of the event itself.
Matt.
So I apologize for missing the beginning, so I probably missed crucial information. My impression is that you divide the Pacific into defining PDO in the northern part, and then there's ENSO, and sort of a perhaps a false partition, because most often for the whole Pacific Basin, we see an eastward open chevron of SSTs with bright spots off of Chile and Alaska, versus then that pattern along the coast there of El Niños. So it goes back and forth between those two Pacific states. If you looked at it from a kind of a unified EOF over the whole basin, would it be different or easier to understand?
So there is another climate index that is called the Interdecadal Pacific Oscillation, or IPO, and that is exactly that. So it looks at the entire Pacific Basin, and it is related to the PDO index. There is a lot of relationship between them. The hemispheres can do different things. Under conditions like you said, maybe if there's a strong El Nino signal from the Central Pacific, that signal will propagate in both directions, but in the absence of that, during events like right now where you have that strong forcing, they'll tend to evolve not quite in sync with each other. So the indices aren't exactly the same, but the IPO has received a lot of interest as well, because it covers such a large area of the surface of the Earth. It has a lot of connections to just global mean surface temperature. And so again, I think both the PDO and the IPO are really statistical definitions, and that to understand them in a physical sense, you do have to break down where those physical sources of variability are coming from. It's not something intrinsic to the North Pacific necessarily.
Just out of curiosity, the 2012 paper, they had that rapid drop-off in predictability.
Mm-hmm.
And I might be missing something crucial here, but if it's just, what you show is just persistence, so are they doing way worse than the systems, or?
So what I believe is that they're showing, so this is something that's kind of frustrating when you read these things, but damped persistence is the prediction that I showed, where you have that decay towards a climatological state. You can also just have persistence, where you just predict that the anomalies will stay exactly the same. And so I believe what they're showing is a persistence of the exact same anomalies going forward in time, and that they're roughly matching that persistence. So I guess one way you could put it is that the SMILE system matches damped persistence, which is an improvement over this, which is matching persistence, but it's still underperforming modern fully statistical models that try to predict the BDO.
With that, I think we're running right up to time, so thank you all for the great questions. Thank you again, Evan, for the great talk, and we'll adjourn.